All right, hey calculus kids. If you're watching this video, it means hopefully you just finished up these three objectives, 1.11 through 1.13. So you all just learned how to define and argue for continuity at a point if a function is continuous at a certain point, and how to calculus justify what continuity means. It means you also learned that if functions are not continuous, how can we still say they're continuous over a particular interval? And then last, you just got done kind of reviewing how we identify and remove discontinuities. And then furthermore, you practiced how do we actually make discontinuous functions continuous. And so in this video, I want to preview the next two objectives where it's going to kind of tie into some of your summer homework with end behavior. And just to give you an idea of the difference between limits at infinity and then infinite limits, which sounds similar, but they have a big distinction, an important distinction. So I want to dive on in with that idea, infinite limits versus limits at infinity. So infinite limits are functions that result in vertical asymptotes, and they are if I'm approaching a finite value, so like I'm approaching an actual numerical value like 1, 2, 3, -1, -2, etc. That limit ends up resulting in the y values going off to positive or negative infinity, and that's where you are identifying your vertical asymptotes with calculus language. That's contrary to limits at infinity, which is I'm actually wondering about the end behavior of the function as I get to super big positive x values or super small negative x values. I wonder where the function, the y values go at those values, and that's where we find our horizontal asymptotes. So let's start by analyzing infinite limits with this function. This is a pretty classic 1 divided by x, and we can see, get my annotation tools, I should have been ready, but I wasn't. So we can see right here, the point 1, 1, and then -1, -1 is on this function, which makes sense. If I plug in -1 here, 1 divided by -1 results in -1 for the y. If I plug in +1, I get 1, 1. So what I'm analyzing here first, and now I have to oddly erase that stuff. What I'm trying to analyze here first is just, if I analyze these particular limits as they approach from a certain side, what is the resulting limits? So thinking of this function, if I approach x equals 0, we can clearly see a vertical asymptote at 0. But if I approach 0 from the right side, we can see the y value start to take off, I was going to say north, to more and more positive values. And so that's implying that that limit as we approach x from the right side of 0, that limit would be positive infinity. This would equal, we could say it's positive infinity. You've heard this called unbounded. Some people even argue like if the limit approaches infinity, it really doesn't exist, which is a fair argument. But for our purposes, for calculus AP, we'll say that limit approaches infinity. But from the other side, as we approach 0, you can see me drawing here. So we approach 0 from the left side, so I'm getting closer and closer to where x equals 0, but I never quite approach it, and I seem to be taking off towards negative infinity. And so what's interesting, our same limit rules still hold, that the exact limit at that value, we'd say, does not exist because the right and left side of the limits are approaching different y values. Now, let's look over here at limits at infinity, where we actually are wondering, as the x values get super big or super negative, what is the resulting y value? Where does the function seem to approach at those, those limits at infinity? We can see right here, here's the given function f of x. And we can see this dotted purple line right here is right at y equals 2. And this function will get closer and closer as I get to really big negative x values. Think negative trillions, quadrillions, quintillions, etc. And as I approach really big positive x values and think of the same thing but positive version, it looks like the function is approaching the asymptote y equals 2, but it's never going to quite approach it. So what we'd say is that the limit as x approaches infinity is equal to 2. And then the limit as x approaches negative infinity is equal to 2 as well. Now, it's not always the case that horizontal asymptotes approach the exact same value. You can have a function where as x approaches positive infinity, it approaches a certain y value, and as x approaches negative infinity, it approaches a different y value. In this case, they happen to approach the same one, but it's not always a guarantee. And so what we could also do is just to write this out. If I just knew the function but not the graph, what I would essentially be arguing is this. I'm wondering, okay, I want to know the limits of this function. I'm doing that same wondering. I'm going to write f of x just for time's sake, but you'll oftentimes see people write the entire function out. I'm still wondering that same thing. And part of your this objective, 1.14 and 1.15, is you all, instead of being given the graph, how can you just be given these functions and figure out what limits will they approach? Using calculus kind of mixed with end behavior stuff, which you all had worked on previously. Then the last thing I'm going to highlight for this video is it's not always one or the other. Oftentimes functions have both. They have infinite limits and they have limits at infinity because they have vertical asymptotes and they have horizontal asymptotes. And we're kind of looking at that picture right here. Let me zoom out a little bit on this so I can see more sweet. So we can see in this function, I'm going to kind of take some guesses and then do like a quick analysis on the next slide. But looking at this function, it looks like if I try to draw some asymptotes for us, which I can, it looks like right here at x equals 2, it looks like we're seeing an asymptote there. And that does make sense. If we actually solve the denominator, set it equal to 0 and figured out where that equals 0, it would be when the x value is 2. And then similarly, it looks like where x is -2 is also going to be a vertical asymptote. And so the limit language is this. We would be saying, if I wanted to analyze that, I'm wondering, okay, what's the limit as x approaches 2 of the function f of x? Or I'm wondering, what's the limit as x approaches -2 of the function f of x? And notice how if we ask that question, we pretty quickly see, okay, that's an infinite discontinuity. Both those limits wouldn't exist. And so what we'd have to do is say, all right, well, let's analyze them from the left side. So we can see from the left side, as I approach -2 from the left, I go off to, negative infinity. As I approach 2 from the left side, so +2, but from the left side, I seem to approach positive infinity. And then we could also analyze both of them from the right side of those values. So if I analyze, again, -2 from the right side, in that case, I approach positive infinity. And as I approach 2 from the right side, so getting closer and closer to +2 from the right side, I seem to approach negative infinity. So we could actually still find one-sided limits pretty easily, but these exact limits wouldn't exist. And then similarly, we have vertical asymptotes that I just showed off, but in this one we also have a horizontal asymptote, and it looks like right around where y equals 3. And so the limit language we'd be analyzing would be this. We'd be wondering, okay, as x approaches positive infinity, really big values of the function f of x, we could actually say it looks like, I hope I said -3, it looks like the limit approaches -3. And then similarly, if we approached just negative value, I put a little negative sign, as we approach as x goes to negative infinity, it also seems to approach -3 for this limit. And if I scroll down, I'm going to delete all this stuff. If I scroll down, I can see the asymptotes via Desmos. It looks like those are the vertical and the horizontal, the vertical asymptotes and the one horizontal asymptote. And your big challenge in this objective is, how could you have still figured that out with no graphs? How can you just analyze this function using our tools of both pre-calculus, algebra 2, and calculus, and still come to the same conclusion of where the vertical and the horizontal asymptotes was? I'm going to stop sharing. I hope that was helpful. Had fun with these two objectives, and let me know if you have any questions.